Hello everyone, welcome to this SWAM-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing the elementary physics related to the plasma. Since we are going to see how the space plasma it affects our the orbital spacecrafts and what are the issues. So, in this regard we discussed the many topics, and in the last class we discussed the device shielding. So, whenever there is some perturbation or any you are inserting any external charge in the plasma environment. So, the plasma that it reorient itself around the it rerounds around the that external charge and makes a shield around it, makes a shield. So, within this shield this environment is non-neutral, it can be a non-neutral environment. But outside this shield, or it is called the device shield, it is again neutral. What does it mean? That any particle outside the device shield, it will not feel whether there is a non-neutral, that is the effect of the non-neutral charge. So, what is the effect of the charges? The charge will exert the field. So, the field outside this the device shield is not there. So, we have seen that when the lambda d is very large compared to R, that the potential energy, the phi r, it tends to 0. So, when we are considering a point charge, I can assume that this shielding is like a sphere. So, if I want to calculate what is that volume of this sphere, so it will be 4 by 3 pi lambda d cube. So, we will see that while we will deal with the spacecraft, depending on the plasma environment, what is the lambda d. This is very important to know what is the device length. So, in order to design some of the sensors, it is where the charge is it needs a very clean environment, there should not be any charge. So, we will discuss all those things. So, this is the last topic of the plasma physics, which will be required for our this course for to know the plasma environment effect on the spacecraft. I will now summarize whatever we have studied. So, whatever we have studied, this shows the collective nature of the plasma. So, we will see this today, and then we will see what is the collective nature of the velocity, its energy, and the temperature of the plasma. So, this will be the topic of today's discussion. So, what is the collective nature of particles? So, here the particles, they do not behave independently, instead it interacts collectively due to the long range electromagnetic forces. So, this I am just now telling this long range electromagnetic forces, but already we have seen it how this happens, and this is one of the defining characteristics of the plasma, and it distinguishes it from the neutral gases. What is long range interactions? So, here the long range interaction is because of this electric and magnetic fields effect of the motion of the plasma particles. So, this it distinction between a plasma and a normal neutral gas is that the interactions are typically short range, that is for the neutral gases. But for the plasma particles, the influence of each other, this happens over long distances via the mutual Coulomb interactions. So, because of this, it gives the collective nature, because that there is a long range interaction because of the electric as well as the magnetic field, and we have seen that is how the plasma responds to the electric field as well as the magnetic field. And in the last class we have seen the device shielding. This is also a striking difference, and it also shows the collective behavior. Whenever you are trying to perturb the plasma, it re-energizes itself to to restore its neutrality. So, a single charged particle in a plasma is surrounded by a cloud of opposite charges that reduce its electrical field beyond a characteristic distance, which we defined as the Debye length. We have derived the expression for the Debye length, and this shielding is also the collective response of the plasma to the perturbation, and it ensures that the macroscopic electric fields are often suppressed. So, they will be there within some limited volume, outside that thing there is no field present because of this Debye shielding. Then we have seen the plasma oscillations. So, if the electrons are displaced from their equilibrium positions, which is relative to the ions, they oscillate collectively, that also we have seen, that is, but that is the localized at the plasma frequency. And these plasma waves, or it is also called the Langmuir waves, are the direct result of the collective motion of the charged particles. Now, the quasi neutrality that already we discussed. So, plasma tend to maintain an overall balance of the positive and negative charges over large scales, and that is called the case of neutrality. That we have seen that even if you are trying to bring a charge to imbalance the neutrality, but that is doing only at a particular, it is in a volume which is called the Debye volume or Debye shield. That what just now I said, that the deviations from the neutrality are typically confined to very small regions like the sheath, or this is the Debye shielding. Now, collective response to fields. So, when an external electric or field is applied, the entire plasma responds collectively. That is, we have seen the phenomena like the drifts, then the currents because of the gyrating electrons, then there can be instabilities. All this, it shows the collective response, and this response can lead to complex behaviors like the turbulence, reconnection. We have seen what is the reconnection, which we are discussing in the first module. So, this collective behavior is what allows plasma to exhibit unique phenomena like the magnetic confinement, then solar flares, coronal mass ejection, auroras and fusion reactions. These phenomena, all those phenomena, it cannot be explained by considering individual particles alone. So, that is why these topics are important to understand how this plasma, which is basically a gas of charged particles, how is it different from the neutral gas. Now, we will see that is the velocity energy and the temperature of the plasma species. This will also, it will be useful for our subsequent the discussion about the effect of the plasma environment on the spacecraft. So, now the velocity is related to the kinetic energy. So, the kinetic energy of a particle of mass m moving with a velocity u is E is equal to half m u square. Now, for an assembly of n particles with different kinetic energies, means the n particles, each particle will not have the same velocities. So, for an assembly of n particles with the different velocities, u I, the average kinetic energy is the average kinetic energy per particle, we can write E average is equal to twice n then summation over all the kinetic energies. So, this will be m I then u I square. So, we can show that is it is valid for even the gas also. We can show for any gas whether it is neutral or the charged in thermal equilibrium. Thermal equilibrium means the condition at which there is there is no heat transfer. So, all the particles you can assume they are at a uniform temperature T. At equilibrium at temperature T, at temperature T, the energy per particle will is E average is equal to 3 by 2 kV into T, where again the kV is Boltzmann's constant and T is the absolute temperature. So, a gas when it is in thermal equilibrium, so its velocities, that is the velocity of the different particles, we can assume or it can be shown that it follows a statistical pattern. So, there will be a distribution or the probability distribution of the particles. You can say that if there is the velocity is one velocity b plus delta v, what is the probability that the velocity of a particle will be between these two terms. So, a gas in thermal equilibrium has particle velocities which follow a statistical distribution. Which is commonly known as Maxwell-Boltzmann distribution. So, what this distribution does? So, this distribution describes a range of the velocities and its corresponding probabilities. So, the Maxwell Boltzmann distribution is given by is equal to A exponential is half then m u square divided by k b into t. So, if I write f of u du, so this represents the number of particles per unit volume. With velocity in the range u to u plus delta u. So, you can find the A from this expression. So, if you integrate this f u from minus infinity to plus infinity, means considering all the velocity distribution minus infinity to plus infinity, then I can write n is equal to minus infinity to plus infinity f of u du, and from where, so I can substitute this here and I can find that is the A is equal to n square root of m divided by twice by k b into t. So, here you know that that is the standard expression, that is the integral, standard integral has been used. So, that is minus infinity to plus infinity e to the power minus s square some variable eta square then d of eta, this is equal to root pi by a. So, now accordingly if you compare this expression and this expression here, so you can find this integral. So, just initially we wrote that is the kinetic energy. So, now what this u we are considering, that is we are considering a one dimensional velocity here. So, for a one dimensional velocity, one dimensional case, we can find the average kinetic energy of the particles the average we can find it. So, E average by using that Maxwell distribution function I can write it like that. So, minus infinity to infinity then half m u square then the multiplied by the distribution function f u then du divided by minus infinity to plus infinity f of u du. So, this is actually the total number of particles n. So, this if you substitute the distribution function f u, that is the Maxwell's distribution, one dimensional distribution, I can show this is equal to 1 by k b into t. Now, if you take the three dimensional case, so in that case this the distribution function in case of a three dimensional problem, the Maxwell distribution it will become like so. So, this now will have a three components. So, I can write this is equal to 4 pi n, then m twice pi k b into t to the power 3 by 2 multiplied by v square and then exponential. So, this expression for the probability distribution function will change here, minus m b square, and the argument of the exponential, this remains the same. So, next we can find the average kinetic energy E v is equal to, again we will use the same expression, minus infinity to plus infinity, then half m v square, then f v d v divided by minus infinity to plus infinity f v d v. So, this shows you can again substitute this distribution function and carry out the both the integration in the numerator and denominator, and you can write this is equal to 3 by 2 k v into t, which we wrote initially. Now, the probability that a particle has a velocity between v and v plus delta v you can write. So, this I will write f v g v, and then we have to divide it by n. So, it will be f v d v. So, this is equal to 4 pi multiplied by b square and then the exponential term. So, that will come minus m b square divided by 2 k v into t. Okay. So, this is the distribution function, and this is the probability that a particle will have a velocity between this. Now, if I know this, then we can find the average velocity, then the RMS, all those things we can find it out. So, average velocity, I can find the average velocity So, average velocity will be, so it is also called the expectation in statistics. So, we can find this is minus infinity to plus infinity, and here b is the random variable. So, v f v d v, and this we can show this is equal to 8 k b t divided by pi m, and we can find the RMS speed. This is the RMS velocity. So, what is RMS velocity? So, V RMS. So, this is the square root of the, that is we take the second moment. So, it is V square f v g v, and this we can show this is equal to 3 k v t by m. So, if I draw that distribution function, that is the velocity and its probability of this Boltzmann-Maxwell's equation, it will look like something like this. So, it will be something like that. So, if in this axis it shows that is the velocity divided by the average velocity. Average velocity. We have already found the expression for the average velocity, and this at this point it is 0, then I can put 0.5, and here it is 1. So, you see that at the mean, that is you are having the peak value, then it is 1.5, then 2, then 2.5, like that it will go, and in this axis you will have all the this is the probability. So, this is called the probability distribution. So, different you can compute it substituting in this those expressions, taking the different values of the mass and all those things, and then taking the computing the average velocity, and then you can compute it to get what is the probability at different velocity function. So, what is important to see from here, that is there are the particles which are substantial particles are there, which does have the velocity more than the mean value. So, this is the mean value. So, if I know this distribution, then it is possible to calculate the velocity distribution. Once I know the velocity distribution, we will see that we will be able to calculate the what is the plasma flux or plasma effluence. So, that is why these topics are very important. We will use it subsequent in our topics of when we are going to see how the plasma affects our spacecraft. So, with this I will end it here. Thank you very much.